Okay, so question 6, we've got a spring on a table, and we can see that they're adding weights here, and that's compressing the spring, and then they're measuring that compression. So remember, this is going to be related to Hooke's law. So we can either stretch a spring or compress a spring. And it says, estimate the original length of the spring as shown in 14. So I'm just going to go across there, oops, and maybe with a better line than that, Rayside. And I've got 52-ish, bearing in mind that line goes up. So 52, and the mark scheme says anywhere between 50 and 55, because clearly you could use a ruler rather than my shaky, dodgy line. Describe how the reduction in the length of the spring when weights are added can be determined. So, well, we know that it's starting at 52, and as long as we take it from the same place, and we'll go there, we've just got to subtract the two values. And the same for here, we know it starts at 52, and then we subtract the two values. So note the original length and the squashed length, subtract the values. State 2 ways the experimental procedure could be improved. Well, one of the things we can see straight away is they've only used 2 weights, or 2 sets of weights, depending on what they are. So we can definitely increase the range of results. The other part is this scale we're having to estimate in between there. If we had smaller increments in between, that would improve it. And there's the 2 main ways. Increase the range of results, we've only got 2. And the other one that always comes up is repeat and calculate a mean. That always comes up. So any 2 of these. Use a ruler with smaller intervals. Extend the range of results by using more masses rather than the just 2 results we got there. One of the things we could do is we could actually sellotape a little pointer, and then that could help us read off the scale. Glue a little stick on. Or repeat the results and calculate a mean. Give one reason why the reduction in length eventually reaches a limit. Well, we're squashing this together, so eventually we'll get to the point where the coils are all touching. There's just no space between them, and then it can't go any further. So the coils are touching, so no further compression possible. And now we've got a different spring is extended. A force of 0.5 newtons is used. Happy with that. An extension of 13 millimeters. That's going to need to be divided by 1,000. And calculate the spring constant. So we're going to need our Kentucky Fried X-rays. So Kentucky Fried X-rays, and it says calculate the spring constant K. So no, K equals F over X. So K equals F over X. K equals the 0.5 divided by the 0.013, and we've got the spring constant 38.5. Then we've got another one. So another spring is extended this time. The work done is 0.14 joules. Happy with that. The spring constant is 175 newtons per meter. Happy with that. And it says calculate the extension of the spring. So the work done, that is the elastic potential energy. So we know that work is equivalent to energy. And we know that the elastic potential energy equals half kx squared. So we want to work out the extension. So if I just quickly go through that now, we want to get x on its own. So move that, divide, or the best way to get rid of a half is multiply both sides by 2. So we've got 2 EPE. That's now gone. We've got the k, so divide by k. Done. And then the next part is we don't want x squared. So the opposite of squaring is square rooting, and then we're ready. So x equals the square root of 2 EPE over k. So here we go. So x equals 2 EPE over k. We're going to take 2 lots of 0.14 is 0.28. You can see that there. And then divide by the 175. You can see that there. And then square root the answer. And you'll be left with an answer of 0.04 meters or 4 centimeters.